Section 5.1, Finding the Inverse. In this section, the goals are, first, what is the inverse of a function? Then we'll talk about types of functions called one-to-one functions and see how we can apply what's called the horizontal line test. Then we'll discuss more in depth what we mean by the inverse function, the notation we use for that, how to find an inverse symbolically and graphically, and how we can restrict domain to find an inverse. And we'll look at an application. So what is an inverse? Well, consider these tables. So in the first table, our inputs are 5, 7, 8, and 10. And our corresponding outputs are -4, 5, -18, and 12. So notice that 5, the input of 5 goes to 4, the input of 8 goes to -18. Now if we look at this second table, notice how the input of -4 goes to 5. The input of -18 goes to 8. It has inverted the ordered pairs of the original function. Now let's consider these functions in symbols. We have f of x is 2x minus 5 and g of x is 1/2 x plus 5 halves. Well, just take for example, how about f of 4? Notice that f of 4 is 2 times 4 minus 5. So that's 8 minus 5, that's 3. f of 4 is 3. Now, what about g of x? What if I were to evaluate g of 3? Well, g of 3 would be 1/2 of 3 plus 5 halves. And that's 3 halves plus 5 halves, which is 8 halves, which is 4. And g of 3 is 4. Now, I can do this with other values. Just for example, let's just do one more. How about f of 10? f of 10 would be 2 times 10. That's 20 minus 5 is 15. f of 10 is 15. And g of 15 would be 1/2 of 15. That would be 15 halves plus 5 halves. That's 20 over 2, which is 10. g of 15 is 10. So these functions undo each other in a sense, or they invert the ordered pairs, right? For f, we had the ordered pair 10, 15. For g, we had the ordered pair 15, 10. And we could do that with many different values of x. So then the question sometimes comes up, will the inverse of a function always be a function? Well, now notice, let's take for example the function f of x is x squared plus 1. Notice that f of 2 is 2 squared plus 1, so f of 2 is 5. What about -2? f of -2 would be -2 squared plus 1, and so f of -2, is also 5. Well, now suppose that this function has an inverse. So suppose that this f has an inverse g of x. Suppose that f of x has an inverse called g of x. Well, then by this concept of inverses, then we would have to have that g of 5 equals 2 and g of 5 equals -2. Well, wait a second. If we remember what we mean by a function, this is not a function, because this input 5 is going to two different outputs. So if we made that supposition that f has an inverse g, we find that g is not a function, right? g of x, so g is not a function. All right, so this is an important concept when dealing with inverses. Not every function has an inverse that is also a function. So we want to talk about certain kinds of functions, what we call one-to-one functions. A function f is called one-to-one if for any elements x1 and x2 in its domain, when x1 is not equal to x2, then f of x1 is not equal to f of x2. So in a one-to-one function, different inputs will always produce different outputs. So the example we just saw a moment ago, f of x is x squared plus 1, is not one-to-one because x1, if we take x1 and x2 to be 2 and negative 2, obviously 2 is not equal to negative 2, but f of 2 is equal to f of negative 2. So f of x is x squared plus 1 is not a one-to-one function because different inputs did not produce different outputs. All right, so is this function one-to-one? F of x is equal to 4 plus 1/2 x. So the question is, really, are there two inputs that give you the same output? 4 plus 1/2 x. And we can sort of think, graphically sometimes. If we think of the graph of 4 plus 1/2 x, that's a line with a slope of 1/2 and a y-intercept of 4. And you might ask yourself, is the output ever the same? Is the output ever the same? Can I ever get that output again? Can I ever get this output again? And the answer is no. So yes, this function is one-to-one. F of x is equal to 2 times the absolute value of x. Now this one, we could think graphically. We can also think symbolically. Notice, for example, that what's f of 3? F of 3 would be 2 times the absolute value of 3, which is 6. And f of negative 3 would be 2 times the absolute value of negative 3, which is 2 times 3, which is also 6. This is not one-to-one. If we wanted to think graphically, 2 times the absolute value of x graphs as a V shape. And just for example, if we were to say that this is 6, here we see that we have these two outputs on that level. Not one-to-one. So in the previous two examples, I really used a graphical perspective to help you see if the function was one-to-one. And in fact, there's a special test for it. If we can create the graph of a function, we can test to see if it is a one-to-one function. A function is one-to-one if no horizontal line intersects this graph more than once. And so we can use this test to see if a function is one-to-one. All right, consider f of x is negative absolute of x minus 6. Using the skills that we've learned in a previous chapter, negative absolute of x minus 6 is a V shape shifted 6 to the right and opening down. So roughly, we're going to get a graph like this. All right, so now, horizontal line test. If no horizontal line intersects its graph more than once, well, here's a horizontal line. It intersects the graph twice. This is not one-to-one. F of x is equal to 2 plus the cube root of x. All right, so that's the cube root function shifted up 2 units. All right, so we get a graph that does something like this. Horizontal line test. Pass a horizontal line. Does it touch more than one point? Nope. How about another one? Nope. How about another one? All right, so any horizontal line that I pass over this curve only touches at one point. This is a one-to-one function. All right, so a little bit about notation. If f is a one-to-one function with ordered pairs x, y, then the inverse of f denoted f inverse. So notice the notation there. We say that f inverse. We don't say f to the negative first. We say f inverse. F inverse is also a one-to-one function with ordered pairs yx. So the inverse of a function is the set of ordered pairs obtained when we swap the inputs and the outputs in the original function. Since we're swapping the inputs and outputs, it should make sense that the domain and range swap. Okay? So if we start with our function f, the range of f is the domain of the inverse. The domain of f is the range of the inverse. And again, we read that notation as f inverse. Caution. F inverse of x is not the same as 1 over the function. All right, so we have to understand this is a different notation. We've learned in the past that negative exponents can be used for to think of reciprocals. This is not a negative exponent. It's a notation that we use for functions. So be careful. All right, determine if the function is one-to-one. If it is, find its inverse. All right, so here we see this function, and we just have a set of ordered pairs. So f of x is the set of ordered pairs. Negative 11, 63, negative 4, 28, 5, negative 17, and 8, negative 32. Now it is a function because no inputs are repeated, but now let's also consider the outputs. 63, 28, negative 17, negative 32. Is it one-to-one? Yes, it is, because no outputs are repeated. So then its inverse, f inverse of x, would be the set of ordered pairs 63, negative 11, 28, negative 4, negative 17, 5, and negative 32, 8. G of x is 7x minus 4. Is it one-to-one? If it is, find its inverse. Well, just producing a brief sketch of this function, it is a linear function. 7x minus 4 would do something like that. There's f of x is 7, or g of x is 7x minus 4, and it appears to pass the horizontal line test. This is a one-to-one function. All right, so now, how to find its inverse? All right, so here's the procedure we'll use. First thing we do is replace the g of x with y. So I'm going to rewrite this as y equals 7x minus 4. Now, we want to find the inverse, so we will invert the variables. All right, so I'm going to invert the variables. And I'm going to rewrite this as x equals 7y minus 4. Now, I'm going to solve for y. So I will add 4 to both sides. X plus 4 equals 7, y. And I'll divide through by 7. So then 1/7 x plus 4/7 is y. I've isolated the y, and so now I will rewrite this using inverse notation. And so I'll replace the y with g inverse of x. G inverse of x is 1/7 x plus 4/7. All right, let's look at another one. H of x is 2 times the quantity x minus 5 square. All right, so I recognize that as a transformation of the basic quadratic function, shifted 5 right, opening up, just a different scale factor, so I get a parabola opening up. Using the horizontal line test, this is not one-to-one. So we will not try to determine its inverse at this point. All right, what about j of x? J of x is 2 times x minus 5 cubed. All right, well, if we, again, think graphically, this is a transformation of the cubic function, and so we would get a graph that does this. And this passes the horizontal line test. It is a one-to-one function. Let's determine its inverse. So then y equals 2 by x minus 5 cubed. Invert the variables. Right? Let's invert the y and the x. I will write this as x equals 2 times y minus 5 cubed. And now I want to solve for y. I'll divide by 2. X over 2 is equal to y minus 5 cubed. I will take the cube root of both sides. Cube root of x over 2 is equal to y minus 5. And I'll add 5 to both sides. And y is equal to the cube root of x over 2, add 5. Writing this in inverse function notation, j inverse of x is the cube root of x over 2, add 5. Determine if the function is one-to-one. If it is, find its inverse. And here we have k of x is x plus 3 over x minus 2. Now this one we haven't learned how to sketch by hand, so let's bring out a calculator. Alright, so there's our calculator. I'm going to go to the y equals screen, and I'll type this in as the quantity x plus 3, close the quantity, divide by the quantity x minus 2, and close the quantity. And I'm just going to graph this in this standard window. And I see this shape. Now, we do see here a vertical asymptote. We'll talk more about that when we get to a later chapter. But remember, what we want to understand there is it's not really part of the graph. It is an artifact left over from the graphing process, but it's not really part of the graph. So if we sort of look at this graph and we think about the horizontal line test, if we were to kind of draw horizontal lines, it looks like it's a one-to-one function. Alright, so it appears to be one-to-one. So then let's try to find its inverse. So then y equals x plus 3 over x minus 2. Let's invert the variables. X equals y plus 3 over y minus 2. Alright, so now to solve this, first thing I'm going to do is get rid of that fraction. I'm going to multiply by y minus 2 on both sides. So I have x times y minus 2. That's x, y minus 2x, and we have y plus 3 on the right-hand side. Now I want to solve for y. So I'm going to get everything with the y on one side and everything without the y on the other side. I'm going to bring everything with the y to the left. So let me subtract y from both sides. And I'm going to bring everything without the y on the right-hand side. So let me add 2x to both sides. So then I have x, y minus y is equal to 2x plus 3. Now notice I have a common factor of y on the left-hand side, so I can write that as y times x minus 1, and the right-hand side is 2x plus 3, dividing through by x minus 1, y equals 2x plus 3 over x minus 1. So then putting that all together, k inverse of x is 2x plus 3 over x minus 1. All right, what if we have just a graph and we're asked to find the inverse? We could try to figure out the function symbolically, and that would probably work with either of these since these are transformations of basic functions. But what if it wasn't one of our basic functions? If all we need is the graph, what we can do is invert the ordered pairs. So notice I have the ordered pair 0, negative 8. Well, that means that the inverse would have the point negative 8, 0. I have the point 2, 0. Well, then the inverse would have the point 0, 2. I have the point 4, 8. The inverse would have the point 8, 4. Now, our given function was a line, so it seems reasonable then that the inverse would also be a line, and so in purple, there's the graph of the inverse function. F inverse x. All right, and we could do something similar with this graph in the second grid. A little bit nastier, but we can work with it. So just find some points. Let's see, I have negative 8 and a little bit more than 6. All right, so then go to the point a little bit more than 6, comma, negative 8. Let's see, what's another good point? Let's see, it looks like I have the point negative 1, 5, or some pretty close to it. So I would go to 5, negative 1. Let's see, I have 2, 2. And so then its inverse would also be 2, 2. I have 3, 0 in blue, so let me plot the point 0, 3. Let's see, I have 7, negative 1.4 maybe. So I need the point negative 1.4, comma, 7. And so we would see a graph that does roughly this. And so there's the inverse function. Now, something that's sort of important about the graph of a function and its inverse is that they have a symmetry. Since we're basically interchanging the variables, we get the symmetry about the line y equals x. So if we draw the line y equals x, we should see a symmetry between those two functions. So notice that, in a sense, I could flip the curves over that red line and get a mirror image of the curve. All right, so f and f inverse are symmetric about the line y equals x. Earlier, we considered the function h of x was 2 times x minus 5 squared. And I created a rough sketch of the function. And so a rough sketch of the function gives you something like this. So it's the vertex at 5, 0, and some other points. And we saw that this is not a one-to-one function. But if we restrict the domain, so what if we kind of cut the graph in half? What if we cut it right there at x equals 5? So what if we restrict the domain to x is greater than or equal to 5? So basically now, we're kind of erasing the left half of that curve. And now if we think about this, we have a one-to-one function. Right? Because it's only touching one point on the curve at any time. Okay, so if we restrict the domain to x is greater than or equal to 5, then y is greater than or equal to 0. Let's kind of remember that. That's our domain and range now. All right, then we can find the inverse. So y would equal 2 times x minus 5 squared. So inverting the variables, x would equal 2 times y minus 5 squared. Solving for x. X over 2 is y minus 5 squared. Square root. Now here's where you have to be careful, because remember when you apply the square roots we get plus or minus. So now we have to decide, do we get the positive root or the negative root? Well, if we think of the inverse, if we think graphically of the inverse now, we would want the points, let's say 5, 0. We had 5, 0 before, so we would want 0, 5. And we would have the point, 6, 6, 2. This point is 6, 2, roughly. So then we would need the point 2, 6. So we're going to get a curve that does this. So is that the upper? I mean, if we think of how the square root function works, is that a positive square root or a negative square root? And it's a positive square root. So we will just keep the plus on the square root, and we'll add 5 to both sides. So then y would equal the square root of x over 2 plus 5. And so then if we restrict the domain, then we can find that H inverse is the square root of x over 2 plus 5 on domain. Now what's our domain? Our domain would be 0, infinity. Right? We've inverted those. Right, we restricted the domain of the original function at x is greater than or equal to 5. Our corresponding range was y is greater than or equal to 0. So now we invert those. The domain would be 0 to infinity, and the range then would be 5 to infinity. And we'll finish the section with an application. Miguel travels frequently due to his management position at work, and has noticed that gas prices continue to increase. To save money, he trades in his V8 pickup truck for a 4-cylinder compact car. The total loan, interest included, is $24,222 over a 66-month period. His monthly payment will be $367, with the outstanding amount denoted by f of x is 24,222 minus 367x, where x is the number of months paid towards the loan. Find f of 60 and interpret its meaning. Alright, well then f of 60 would be 24,222 minus 367 over times 60. I'll use a calculator here. So 24,222 subtract 367 by 60 is 2,202. Interpret the meaning. After 60 months, the outstanding amount owed on the loan is $2,202. All right, find the inverse of the function. All right, so let's rewrite it as y equals 24,222 minus 367x. Invert the variables. X equals 24,222 minus 367y. Solve for y. X minus 24,222 is equal to negative 367y. So then, dividing through by negative 367, y would equal x minus 24,222 over negative 367. Let's rewrite that using inverse notation. F inverse of x is x minus 24,222 over negative 367. Find F inverse of 11,377 and interpret its meaning. F inverse of 11,377 would be 11,377 subtract 24,222 divided by negative 367. I'll use a calculator here. 11,000, let's put this in parentheses, 11,377. Subtract 24,222 and divide that by negative 367, and we get 35. Oh, I wrote 37, that should be a 35. All right, yep. So, interpretation. Well, now our domain and range have inverted, so this is now a dollar amount, and this is a number of months. So, the amount outstanding will be $11,377 after 35 months. All right, that concludes the presentation for this section.